Hi, this is Mrs. Evans, and welcome to part 2 of Antiderivatives and Indefinite Integration. In the last part, we started to work a little bit with our derivatives just to remind ourselves the patterns, and so then that way it would give us the opportunity to work backward. So what we're going to do now is we're going to work a little bit with some integration formulas and some ways to think backward. So let's start with the very first one. The very first one is the antiderivative of 0 dx. And what I want you to do is think like Jeopardy. What type of problem would you take the derivative of and get 0? So when I think about that, I think of a lot of different ones. I could do the derivative with respect to x of 7. If I did the derivative with respect to x of 7, I would get 0. If I did the derivative with respect to x of 70, I would get 0. If I did the derivative with respect to x of negative 70, I'd get a 0. So what that's telling me is it doesn't matter what this constant is. Whatever that constant is, when I take the derivative, I'm going to get 0. So generally, I know that the antiderivative of dx, the antiderivative of 0 dx is equal to c, a constant. Well, I'm going to think the same way with this next problem. On this next problem, I'm going to take the antiderivative of K dx. So I'm going to think of some examples. If I did the derivative with respect to x of negative 10x, my answer would be negative 10. If I did the derivative with respect to x of positive 100x, my answer would be positive 100. So what I keep getting here is instead of 0, I keep getting a constant right here. Well, what causes me to get a constant is when I have that constant times just plain old x. So what I know is that the antiderivative of k dx is kx plus c. Now, where did that plus c come from? Do you remember? Well, what you need to remember is in all of these problems right here, when I was taking the derivative with respect to x of 100x, sorry, my pen's not working, I could have had minus 200. And if I would have had a minus 200 here, I still would have gotten 100 for my derivative. If I would have had 100x plus 1200, I still would have gotten 100. So this plus c ensures me that I get all the answers that it could possibly be. Now in my next one, this one we're not going to think backwards, but what we're actually going to do with this next one is we're going to think about how this relates to the constant multiple rule with derivatives. When I did the constant multiple rule with the derivatives, if I had k f of x, what I knew when I took the derivative was I could get k f prime of x. And what that meant was that I just took the derivative of the function and left the constant to the outside. Well, what's nice is it works the same way with antiderivatives. If I'm doing an antiderivative, and this is helpful in a lot of cases, instead of worrying about taking the antiderivative with the constant in there, I could pull the constant to the outside. And when I do that, I have just to take the antiderivative of the function on the inside. And that'll be helpful in a lot of different cases. Same thing works with this sum and difference formula. If I have the antiderivative of f of x plus or minus the antiderivative of g of x, I can actually split it into the antiderivative of each part. And that is very helpful to do when you're taking antiderivatives. Now our last one is our power rule. Like before, we have a power rule when it comes to antiderivatives. And I just want to remind you that our power rule for derivatives was that we had to multiply by the exponent, get my pen to work here, multiply by the exponent, and then subtract the exponent by 1. Well, when we're doing the antiderivative and we're doing the inverse, we're going to go completely backwards. We're going to start here and do the inverse. So instead of subtracting the exponent by 1, we're actually going to add 1 to the exponent. And then instead of multiplying by the exponent, we're going to divide by the new exponent. And that might sound kind of confusing, but here's really what it looks like. What you do is you take this exponent right here and you add 1 and you get x to the n plus 1. Now I have a new exponent. The new exponent is n plus 1. And so I divide by that same new exponent. So the top and the bottom are going to look the same until, of course, you reduce them. And I can't forget my plus c. Now what I have to remember in this case is that in this power rule, n cannot be equal to -1. Can you tell why? Let me erase real quick so you can look. In this problem right here, if I let n be equal to -1, I'd have -1 plus 0 on the bottom, which would give me a 0 in the denominator. This comes up when you have 1 over x dx, because that would make this x to the -1. This particular problem has a very unique answer that we're going to come up with later. We're not going to worry about that now. So for right now, we cannot solve this type of problem. We have to wait till a little bit later. But for now, that is all of our integration formulas and rules. So let's use some of those rules to actually do a problem. And just like with derivatives, the trick to taking an antiderivative is you have to be able to rewrite it into something that you can take the antiderivative of. If you look at this right now, we don't have any rules for when we have a composite function. Do you remember that when you have insides, that's called a composite function? When we did derivatives, we did something called the chain rule. Well, now what we're going to have to do is we have to rewrite by multiplying this out. And what you could do is you could come over to the side and you could write this out and then FOIL if you'd like, or some people like to call it a double distribute. But basically what you're doing is you're going to take and multiply everything in this parenthesis by everything in that parenthesis. But I think there's an easier way to do this. The easier way I think to do it is to remember that there's a shortcut. The shortcut is to think about squaring the first term, then multiplying and doubling the first and the second term, and then squaring the last term. And this is what it looks like. There we go. If you square the first term, you get 4x squared. If you multiply and double these, you get, if you multiply those, you get 6x, and if you double it, you get 12x. If you square the last term, you get a 9. So the reason why you want to do that shortcut is you can actually do it in your head rather than having to go off to the side and FOIL it all out. Now, what I can do from here is I can use my sum and difference formula, or my rule that tells me that I can split a function that has the sum and the difference in the middle into different pieces. And one other thing I could do if I wanted to is I could pull out a 4 and take the antiderivative of x squared dx. And then I could pull out the 12 and take the antiderivative of x dx. And then I could leave the 9 in there if I want, or I could even pull out the 9 and take the antiderivative of just plain old dx. But I'll tell you, sometimes that confuses people, so I like to leave it inside most of the time. So let me get rid of that right there. So when you take the antiderivative of these, what you're actually going to do is these are power rules. So you're going to add 1, and I'm going to have a 3 here. And what that's going to do then is give me my new exponent, and then I'm going to have to divide by that 3. So here's what it looks like. You have 4/3 x to the third. See where that comes from? Here's my x to the third. I'm dividing by the exponent, my new exponent, and I still had a 4 to the outside. Now on this one, this is the exponent of 1. I'm going to add 1 to it, and it's going to give me x squared. Ooh, my pen's not working. And I have to divide by 2, and I'm going to multiply by 12. Well, the 12 and the 2 cancel, and the 12 and the 2 can't, and reduce to a 6. So my next part is plus 6x squared. Then when I do this one over here, this is like having 9x to the 0 power. Let me erase that so you can see that a little bit better. It's the same thing as having 9 times x to the 0. I add 1, that gives me x to the first, and I divide by 1. And that's just going to give me a 9x. So I'm going to have for this one a plus 9x. And the thing I can't forget is that anytime I do an antiderivative, I have to add a plus c, because any one of these could have a constant on the end. So that's my final answer. So here's another one that we need to rewrite. Do you remember how you used to rewrite this when you did a derivative? Instead of writing it as the square root of x, what you would do is you would write it as x to the 1/2 power. So with our new rule, what we're going to do is we're going to add 1 to our exponent, which is going to give us x to the 1/2 plus a 2/2. And we have to remember that whenever we get a new exponent like this, that's what we divide by. So we end up getting x to the 1/2 plus 2/2 divided by 1/2 plus 2/2, which simplifies into x to the 3/2 over 3/2. And whenever you have a fraction like this in the bottom, what you can do is flip it over and multiply by the reciprocal of this. So what you're going to end up having is 2/3 x to the 3/2, and you can't forget your plus c.